Good morning, everyone. Welcome back to Computer Science 150. Today, I'm going to be starting a series of two lectures that focus on the subject of loops in Java. This covers material that you'll find in Chapter 5, and if you click on the lecture notes for today, you'll see that I have suggested reading for you, sections 5.1 through 5.9. And again, since these lecture notes are fairly lengthy, I anticipate that it'll take me both today and Friday to get all the way through this particular set of lecture notes. And in the meantime, you should be starting your reading with section 5.1 in the textbook. Also on Friday, I'm going to be assigning another programming assignment. This one will come from Chapter 5, so that's yet another reason for you to go ahead and start doing the reading from Chapter 5 in preparation for that. And also next week's lab will focus on some material from Chapter 5. Right, so let's get started with the lecture for today. So today we're introducing a new concept, the concept of a loop in Java. And let's start with the first and most basic example of a loop in Java, this construct called the while loop. And here on the slide, you see the structure of this is fairly straightforward. Like an if statement, the while loop is centered around the test. And very much like an if statement, the first thing that happens when you reach a while statement is that the test will get evaluated. And if the test evaluates to true, you will then go and do whatever statements are in the block of curly braces that come right after the while. Now, what's new here is that the while loop is an example of what's called a repetition structure. So what will happen is if the test evaluates to true, and then you do the statements that are inside the curly braces, what happens next is you come back around and reevaluate the test again. And as long as the test continues to be true, you're going to keep going around in circles, which is why this is called a loop. Right now, in most cases, what's going to happen is that the test will involve some variables, and quite likely the code inside the curly braces is going to be changing those variables. So that opens the possibility that eventually the test will no longer be true. And as soon as the test fails to be true, we'll stop repeating the body of the loop and simply go on to whatever comes next. Now, by far the best way to explain in more detail how this works is to start showing you examples. And the rest of today's lecture and all of Friday's lecture is going to consist of a large number of examples to show you the wide variety of things that you can typically do with this simple construct. The first example we're going to look at is an example that illustrates one particular application of this construct, and this application is called validation. So let's pull up the example and see what validation is and how the while loop can help us do that. All right, so what I brought along here is I have brought along a program very similar to the programming assignment that you most recently did, the assignment to compute wind chills. The only thing that I've done here is I've added some new features to the program. In particular, I've added the idea of validation. All right, so what is validation and how do we do it? Well, validation applies to situations where you are getting inputs from a user. And that's certainly the situation here because in the wind chill program, you have two inputs that you're reading from the user. One is the temperature and the other is the wind speed or the wind velocity. Now, in some cases, when you ask the user for input, there are both valid inputs and invalid inputs. And this program is a nice example of that because in the problem statement, the author told us that the wind chill formula is only valid for certain temperatures and it's only valid for certain wind speeds. So one of the things we have to do is we have to do what's called validating the user's input. And when you validate a user's input, basically what you do is you take a look at the input they provided and you determine whether or not it looks reasonable. Okay? Now, a very common strategy for doing validation is to use a while loop because what the while loop basically allows you to do is it allows you to go back and keep asking the user for input until they get it right. All right, and here's a simple example of this. Here's the part where we ask the user to enter the wind speed. Again, the story with the wind chill formula is that the wind chill formula only applies to wind speeds of 2 miles per hour or greater. So the first thing we want to check is we want to check for an invalid wind speed input. In this case, an invalid wind speed is any wind speed that's less than 2 miles per hour. Right, so we use that as a test in a while construct. And if the test evaluates to true, that means that the user provided us with an invalid wind speed input, and we have to give them another chance to try again. All right, and standard way to do that is to begin by printing a message basically telling them that they have provided the wrong input, and then we give them a second chance. We give them another chance to go ahead and enter a wind speed that is correct. Now, again, if the user is feeling perverse, they can keep entering the wrong input, and all that's going to happen here is we're going to keep going around in circles, because each time they enter a value of V which is not valid, the loop test will determine that it's not valid, and it will take them back through the whole process again. And we're going to keep going around in circles until the user finally decides to enter an input that we would like to see. Right? And we can do that for both of the inputs in this program. We do it both for the wind speed. We also do it for the temperatures, because the temperatures have to fall in a certain range. A valid temperature is between -58 and +41. So if the user enters a temperature which is either below -58 or above 41, that's an invalid temperature, and we have to make them try again. And here the while loop is the ideal construct for doing that. This will give them an opportunity to try entering temperatures as many times as they want until they get it right. And eventually, when the user does enter a temperature that is correct, then this test will fail and we'll go on to whatever comes next. Right? So that's a fairly natural application of the while loop. It basically allows you to keep asking for input until the user finally provides you with an input that looks right. And again, the only other thing to remember in this case is that in the test that goes in the while loop, what you're testing for here is an invalid input, because the idea here is as long as the input keeps looking invalid, we're going to keep coming back and asking and trying to get a valid input. And that's how the while loop is applied in this case. All right, now again, at any point in the lecture today, if you have a question, please feel free to raise your hand and stop me and interrupt me with any questions you have. All right, so this is our first basic application of the while loop. All right, now next, another thing to say in context of talking about loops is that many loops work in association with something else, a thing called a loop counter. And here's a very simple example of a loop which features the use of a loop counter. So what is a loop counter and what does it do for you? Well, in most cases, a loop counter is an integer variable, and its primary purpose is to keep track of how many times you've gone around the loop. Right, so the appropriate way to set this up is before the loop starts, we set up an integer variable. Very often it's n or something like that. And this plays the role of what's called the loop counter. And at the beginning, before we've had any chances to go through the loop, we set that variable to a value of 0. Then below that, we set up the while loop, and the test in the while loop basically refers to the loop counter variable. What's happening in this case is I want to set up a loop that goes around exactly 10 times. So to do that, I'm going to let the loop counter variable keep track of how many times I've gone around, and the loop test will check to see when the loop counter has hit 10. And as long as the loop counter is still less than 10, we're going to keep going around, and eventually when the loop counter does reach 10, we will stop this process. So the loop counter literally controls the repetitions here. It controls how many times we go around. And finally, the other thing that you need in association with a loop counter, and this is usually done at the very end of the while loop, the very last thing you do before you go around for another trip, we make sure that on each trip through the body of the loop, we increase the loop counter by 1. That's the fairly standard way to do that. All right, and then finally, the only other piece that we need here is what you're planning to repeat. And since this is a very basic example, I'm doing something rather silly. What I'm doing here is I'm writing a piece of code that prints a message multiple times. It basically prints the message hello exactly 10 times using the loop structure as a way to repeat that process over and over until you've repeated it exactly as many times as you want. Okay, so that's an example of how to use a loop counter to control how many times you repeat a process. And loop counters, you're going to see these all over the place in examples because they're one of the most popular strategies for controlling the behavior of a loop. They're a very straightforward way of making sure that you do a loop exactly as many times as you wish to go around the loop. That's their primary application. Okay, now let's also take a look at a series of examples where the loop counter also plays a further role in the example, and that is the loop counter also has something to do with what the loop is actually doing, right? In this first example, the only reason the loop counter is there is to make sure that we went around exactly 10 times, but in other examples, the loop counter or the loop control variable also plays a role in what it is we're actually doing or repeating in the loop. And the next example will show us that. All right, so in the next example, we're going back to wind chills again. This time around, I'm going to do something a little bit different. To show you what this version of the program does, let me simply run it and show you what it's meant to do. All right, so in this version, the program is only going to prompt us to enter a temperature. And instead of prompting us to enter a wind speed, what the program will be doing instead is it will be printing a table of wind chills. Oh, sorry, it did ask for, oh, I'm sorry, I accidentally ran the wrong thing. Let me explain what just happened here, because this is something that may happen to you eventually. What just happened here is that I have a project, but I put actually 3 separate programs in it. And the way that most projects are set up is the first program that you put in the project, which was the wind chill, that's the one that automatically gets run when you click the green run button. Right now, in cases where you have multiple programs all in the same project, what you have to do is if you want to run an alternative to the one that runs automatically is you go to that file, go to the source code and right click and choose the command from the right click menu that says run this file. Right, so that's what you'll need to do in cases where you actually have multiple different programs all in the same project. You have to run each one of them separately by using this command here. Okay, so now this version, this will prompt me only to enter a temperature. And instead of them prompting me to enter a velocity, what it will do instead is print a table of wind chills for different velocities. All right, so here's the output it produces. Basically what it does is it runs through a range of different wind speeds running from 2 miles an hour up to 20 miles an hour. And for each of the different wind speeds, it computes and prints the associated wind chill temperature that goes with that. Right, so clearly this is going to be a process that involves some repetition. We're going to need a loop to basically work our way through this range of different wind speeds. So let's take a look at the loop that does the actual work here. All right, so here is the loop. For this purpose, I am actually using what you can sort of interpret as a loop counter variable. In this case, I'm using the wind speed as a loop counter. All right, so to do that, before we drop into the loop, the first thing I do is I set the wind speed equal to the first value that I would like to work with. Then the test in the loop basically says we're going to keep going as long as the wind speed has not exceeded some limit that I had in mind. And in this case, since I want to run from 2 up through 20, the loop was going to keep running as long as the velocity is less than or equal to 20. And eventually when the velocity gets greater than 20, we're simply going to stop because at that point the test will no longer be true. Right? Then on each trip through the loop, what we do is we compute a new value of the wind chill temperature. And you'll notice in this case, the variable that I'm using to control the loop also plays a role in what I'm computing. It's basically the velocity that gets used to compute the wind chill. And then after computing each new combination of velocity and wind chill, we print that. And then as is typical for a loop counter, we change the value of a loop control variable at the end of each trip through the body, right? So after each round, the velocity is going to go up in steps of 2 miles per hour, and that's how you manage to get yourself a table where you print a bunch of different velocities going upwards in steps of 2 miles an hour at a time. All right, so there's another example of using a variable to control a loop. And this is much more typical of control variables in that in many examples, control variables also play a role in what the loop is doing. In this case, the loop is computing values for a table, and the control variable plays a role in the calculation. It actually has an active part to play in what's being done in the loop. All right, so there's an example of using a loop to construct a table. And in that example, one of the parts of the table, the velocity value, also acts as something that controls the behavior of the loop. Okay, now while we're still on this same example, I want to do one variation of this because I want to comment on something that we just did here that doesn't look quite right. As you can see from the table that gets printed, the table actually looks a little bit ugly. One thing that looks particularly ugly is the second column because things get shifted all over the place as we work our way down through the table. One of the things that happens here is that when we shift from 8 miles per hour to 10 miles per hour, the first number takes up more characters than it used to. And a side effect of that is that ends up shoving the second number over to the right a little bit, which basically gives us a column which looks kind of crooked. Another issue that comes into play here is that as we work our way through the table, the temperature values drop from positive values down to negative values. And as soon as we hit negative values, the negatives, the minus signs, also knock things further out of whack. Right? So although we have a table being printed here, it doesn't quite look quite as nice as I would like. So I'm going to show you a second example to illustrate how you can exercise more control over something like printing a table and produce a much more attractive looking result. All right, so I brought along a third program in this project, and the name of this one is Formatted Table, because in this one we're going to be printing a table, but we're going to be doing some tricks to make sure that the result looks much more attractive. So let me simply run this second version and show you what it looks like. Again, we'll enter a temperature, and again, it will print a table. This time around, the table is a lot more attractive. The numbers line up very nicely in very nice columns, and they even do nice things like when the temperatures become negative, the minus signs don't knock everything out of whack. All right, so this is much better as a way of printing a table. The table is much more attractive and much nicer to look at. Let's take a look how I actually made this happen in Java. Right now, there's a specific trick to make something like this happen in Java, and that is to use a special version of the print command. Up until this point, the only versions we've used are either print or print line, and as you saw from the previous example, those don't give you an awful lot of control over exactly what's get printed. Now, in cases where you want to exert a lot more control over what gets printed, there's an alternative. It's called print formatted, or printf for short. And this is a mechanism that allows you to exert a lot more control over exactly what gets printed and how. All right, and here's an example of how printf works. Printf has several parts. So the first part is always a chunk of text, and this text plays a special role. This is what's known as the formatting text. Then following that, we have a list of variables. These basically represent values that we would like to have printed. And for as many values as you would like to print, you basically write a list of variables or other values that you would like to print. In this example, on each row, I want to print 2 values. I want to print a wind speed and the wind chill temperature. Now, the next thing to do is in the text part of this, we have what are called placeholders. And you can identify that something is a placeholder because it starts with a special character. It starts with a % sign. All right, so here, because we're printing 2 values, there are 2 placeholders. And the idea is that eventually when this gets printed, these values will go in place of the placeholders. All right, so the placeholders basically determine where in the text these values are going to be printed. And furthermore, the placeholders give us more control over exactly how these values are going to get printed. All right, and the way we do that is, in addition to the percent sign, there's also some other text here that we use to control the printing. And here's how you interpret this. The next thing you see after the percent sign is a number. And what that number says is how many characters wide we would like this value to be. In this case, I'm using 8. Now, what that's saying is that I'm about to print a number, and I want to make sure that when this number gets printed, the number occupies a total of 8 characters, no matter what happens. All right? And you can see that here, because if you look at the output where the velocities are being printed, for example, if you look at the last one, if you go across and count how many characters are actually here, it turns out there's a total of 8 characters. There are 5 characters in the number itself, counting the decimal point. And to make sure that this occupies a total of 8 characters, this also was automatically padded with an extra 3 spaces on the left. All right, and again, the formatted print command will do that for you automatically. If the thing you're printing isn't 8 characters wide, it will automatically insert extra spaces at the front to make sure that it ends up exactly 8 spaces wide. All right, so that means that each one of these velocity numbers that I print, they're all exactly the same width, and that guarantees that all of these numbers line up very neatly in a column. All right, so that's what the 8 does. Then we put a decimal point indicating that we're going to be printing a decimal number, and after the decimal point we have a number 2 that specifies how many digits we would like to show up after the decimal point. All right, normally in Java, when you print a double, it's going to print quite a few digits after the decimal point, but what this allows us to do is it allows us to control how many decimal values we get. In this case, we're asking for exactly 2 digits after the decimal point, and that again controls the appearance of the number that we're printing. And since I use the same formatting for both of the values that we're printing here, they both get printed in the same way. In both cases, these things occupy exactly 8 spaces. And if the number that we're printing takes up fewer than 8 spaces, it will automatically get padded with spaces to the left so that everything lines up very neatly on the right edge. All right, so this gives you a lot more control over printing numbers, and it's useful for printing numbers. It's also useful for doing things like printing dollar quantities. So for example, if we were printing dollar amounts here, one way you could control the dollar amount is by not specifying how wide the number is, but instead putting a dollar sign in front of it. This would be a way of printing a dollar value so that it has exactly 2 digits after the decimal place, which is handy for printing money values. All right, so there are all kinds of variants of this that you can use for printing things nicely and getting things to line up nicely in a table. And finally, one last thing that shows up in this text is a special character here. At the very end of the text, I typed \n. That's an example of what's called an escape character, and escape characters are used for special purposes. In this case, the escape character that I'm using, the \n, is what's called a new line character. And what it does is it guarantees that there's a line break at the end of the text that I'm printing. All right, and again, you'll need that because when you're using print formatted, unlike print line, which automatically puts a line break at the end of each line, print formatted doesn't put line breaks in unless you tell it to do that. All right, so I have to explicitly put a line break at the end of each line of text that I'm printing because print formatted won't do that for me automatically. Okay, so that is the fabulous print formatted command. There's actually a section in the textbook where you can read in much greater detail about the print formatted command. Off the top of my head, I've forgotten what that section is, but I put that in the lecture notes for today. So if you read down to this example in the lecture notes, you'll see a reference there to one of the sections in the textbook where the author goes into much more detail about all the different things that you can do with printf. All right, it's a very handy and very powerful tool for printing things like table and getting your tables to look very nice and attractive. Okay, so that is that example. And again, if you have questions at any point along the way here, feel free to raise your hand and interrupt me with any questions you have. Okay, now, next example. Let's go take a look at another thing that you can do um, involving a loop counter variable. Here's another example, typical example with a loop counter variable. In this case, we are using a loop counter variable n. Uh, we're using it to control a repetition and do this exactly 15 times. And then at the end of each trip through the loop, we increase the value of the loop counter variable. Here's an alternative way to do that. Instead of typing n equals n plus 1, you can type a shortcut form, which is n plus plus. And on each trip through the loop here, we're using the loop counter variable in combination with a computation that we're doing. In this case, what I'm doing is I'm computing powers of 2. And I'm using the math.pow command to compute 2 to the power n. I'm going to write a bunch of print statements that show here are various powers of 2. Right? So another typical example of using a loop counter or a loop control variable to interact with the thing that you're actually computing. Okay. Oops, and sorry, I've gotten a little bit ahead of myself here. I'm going to come back to this in a minute. Before I do that, I've got one other example that I brought along here in NetBeans. And let me pull up this example. This is yet another example of using a loop counter variable in combination with something that we're doing. Now, in this example, we're doing our first example of a very typical thing that people do with loops. And in this example, for the first time, we're going to see an example of a loop that is designed to implement a search. Searching for things is a very common activity in computer science and in programming. And we're going to be seeing lots of examples where we use loops to basically implement a search process. And here's our first basic example of this. Now, what's going on in this example is we're going to have the user input an integer. And what we're going to try to do in this example is we're going to try to find all of the numbers that divide evenly into that integer, and we're going to print a list of those, right? And to show you how that works, let me go and just run the program and show you how this works in a typical example. So for example, if I enter the number 12 here, 12 has quite a lot of things that divide evenly into it, and this program is designed to search for those numbers and print them, all right? So it prints that 6, 4, 3, and 2 are all numbers that divide evenly into 12. Right, now, to do this process, as you can see, we're basically going to work our way down through a series of numbers. And to do that sort of backward search process, I'm going to be using a loop control variable, d, in this program. D starts out equal to n minus 1. We're basically going to work our way through all of the numbers that are less than n, looking for things that might divide into n. Right, and on each trip through the loop, we're going to take a look at one of these d values, and then after each d value, we're going to go down to the next lowest one by using d minus minus instead of d plus plus. And the whole process will continue as long as d is still greater than 1. Eventually, when d hits 1, we'll stop. That's the last value that we want to work with. Then for each value of d that we come to, we'll use the remainder calculation to look for things that divide evenly into n. Because the story here is that a number d divides evenly into n if there's no remainder after you divide n by d. All right, so remember, to do the remainder operation, we use the percent sign. So this is basically saying if the remainder after we divide d into n is 0, that means that d divides evenly into n. That means we found ourselves a divisor, and then we want to go ahead and print that thing. All right, so very simple but very typical example of using a loop to run a search process. We have a range of values that we want to search through. We use the combination of the loop and the loop control variable to systematically search through that entire range. And then at each thing we come to, we have an if statement that simply asks, is this something that I'm looking for? Have I found a divisor? And if so, let me go ahead and print it. All right, very typical example of a search process. Okay, now the next example we're going to look at is another typical application of loops. Another typical application of loops is using loops to add things up. In some instances, we want to do some arithmetic problems that involve adding up a large number of terms. And especially if you have a very large number of terms, you'll want to automate that process and use a loop to carry out and automate the process of adding this large collection of terms together. So the first example I've brought along those lines is an example that's going to compute this sum here. This is a very famous sum in mathematics. It's called the harmonic sum, and it's based on a very simple pattern. What we're doing here is we're adding a series of fractions, and in each new fraction, the denominator goes up by 1. So what we're going to be doing is adding 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on, all the way up to some upper bound of 1 over n. All right? And since I want to be able to do this for any value of n that the user might input, somebody's going to have to mute. Sounds like somebody's recording and is doing some sound here. Okay, so, and because I want to be able to do this up to any value of n that I would like, we clearly need to automate this process, right? So to automate that process, we'll be using a loop, and here is the code that takes care of doing that. So here's the harmonic sum calculation, and here are all the key pieces of how you would do this. The first thing we need to do is we need to have the user input a value of n. This will determine how many terms get computed, and it will be used as part of the control process, because in the loop, I'll be using a control variable, this integer n, and the process will run as long as the control variable is less than or equal to the capital N that we entered at the beginning. Right? Then, because we're adding stuff up, we're going to need two other obvious parts. One other thing we're going to need is you're going to need a variable that contains the sum, the variable that stores the total, the grand total that we're adding up. And as we go along and as we generate new terms, we're going to be constantly adding new terms to that sum. And another useful thing is that for each new term that we generate, we'll need to have a variable to store that term before we can add it to the sum. So I also have a variable here for that purpose. Okay, so with everything set up here, here's the loop control variable. Here is the test that makes sure that we add up exactly the right number of terms. Then on each trip through the loop, what we do is we compute a new term based on the current value of the loop control variable. We add that term to the running total that we're computing, and then we simply increase the loop control or the loop counter variable by 1. All right, so that fully automates the process of generating all of the terms that we need and adding each new term to the running total that we've generated, and then we simply have to print the sum at the end. And again, since this process is fully automated, I can enter any value of n that I like, even something fairly large like 100 or even 1,000. This will go through and automate the process of adding up all of those terms and giving me a correct value for the summation. Okay, so a very powerful application of loops. Loops make it possible to automate lots of things, including adding up huge numbers of terms. So I can do this for 100 terms. I can do it equally well for 1,000 terms. It's really no difference as far as I'm concerned. It just takes a slightly longer to compute. And by automating the process, we can add up 1,000 terms in a sum in a very slick and automated way. All right, so that's another typical application of doing an automation process involving a sum. Okay, now, let's see. Here's another closely related example. This is very similar to the last example. The only difference in this next example is the nature of the sum that we're computing. Here's another very, very famous sum in mathematics. Those of you who have taken a calculus course, especially if you've taken a Calculus 2 course, you may have encountered this sum before. In the limit, as n gets very large, this sum approaches a famous number in mathematics. It approaches the number e. Right? And what's going on in the sum here is that the denominators in each one of these fractions are what are called factorials. A factorial is actually a product. For example, n factorial is the product of n times n minus 1 times n minus 2 all the way down to 1. And having the factorials in the terms changes the structure of these terms that we're adding up. Okay, now also having the factorials in these terms makes the individual terms harder to build. So when we write a program to compute this sum, it's going to be a little bit more tricky to compute the individual terms that go into the summation. So let's take a look at that example and see how we generate those terms. Okay, now what you're going to see in this case, somewhat interestingly, is that the code in this example doesn't look very different than the last example. And for one reason, it has a lot of features in common. For one thing, we still have a control variable. It's still called n. We still have the user inputting an upper bound for us, the capital N, and those two together control the loop, how many terms we need to compute. Again, the story is on each trip through the loop, we're going to be computing a new term and adding it to a running total by doing something like this. And of course, on each trip through the loop, we're going to be increasing the value of n. Okay, now, the one thing that changes here is the procedure for computing each individual term. Let me show you an alternative way that we could have done this. To make this closer to the last example, what I could have done instead here is right before it's time to add each new term to the summation, I would have to compute that term. All right, so in this case, that would mean computing a fraction, 1 divided by something. And to make sure I don't accidentally get integer division, I need to make sure the 1 looks like that. The only complication here is that the thing in the denominator needs to be a factorial. So maybe we might guess that there is a function in the math set of functions that will do this. Is there a factorial function? Unfortunately and sadly, no. When I try to do that, it turns out that even though the math collection has a lot of useful functions in it, the factorial function is not one of the functions that's available. So that means I can't compute the term doing this. Instead, I'm going to have to do something a little bit more clever. All right, here's what I do. The first thing that I do is I take advantage of the fact that the first term in the summation here that I'm adding up is actually quite simple. Because 1 factorial is just 1, the first term I have to compute is just 1 divided by 1, or 1. All right, so that means when the process starts, the first term that I'm going to need is actually pretty simple. It's 1. So I go ahead and you do that right away. So on the first trip through the loop, I take the running total, which is already set to 1, and I add the first term to it. So we're good at least for the first term. Now what's going to happen next is we're going to go to the second term. Now here's what happens when we go from the first term to the second term. The factorial changes. We shift from having 1 factorial to 2 factorial. Now, when that factorial changes, the main thing that's different is that we basically have added a new factor onto the front of the multiplication. Previously, this multiplication just looked like 1. In the next round, it's going to look like 2 times 1. And in the round after that, it's going to look like 3 times 2 times 1. And what that tells me is that on each new round, this part of the division is going to have 1 new factor in it, and that new factor each time always turns out to be n. So the trick is, if you knew what the previous divisor was, to get the next divisor, you simply take the previous divisor and you multiply it by n. Or another way to express this mathematically is if you knew what the previous term was, you could get the next term by multiplying the previous term by 1 over n. All right, so that actually makes it a little bit easier to make each new term. The simple trick is to make each new term, you take the previous term and you multiply it by 1 over n, or you take the previous term and you divide it by n. That's a simple rule for making each new term in the sum. All right, so that's a somewhat slick and clever way to work around the fact that we don't have a factorial function that we could use to compute the individual terms. Instead, we notice that the individual terms follow a predictable pattern, and we use that pattern to make each new term from the one that came before it using a very predictable process. Okay, and the final thing to do with this example is to run it and show you that it actually works. If you know what the number e is, you know roughly what to expect for the output here. So let's compute this up to 100 terms. And here, what I'm having at print is both the result of the summation and what the actual number e is. And as you can see, it does a pretty good job of approximating this out to as many digits as we've got. It looks like the summation has hit the number e exactly right. Okay, so that lets me know that we got the summation set up correctly, and this example is working exactly the way that it should. Okay, we've got just 5 minutes left, and in the last 5 minutes, I've got one last example to show you today, and then on Friday, we'll be continuing with more examples. But the last example that I brought for you today is an example of another key idea that sometimes gets used in combination with a loop, and this is a construct known as the break statement. Right, now, here's what a break statement is used for. Under normal circumstances, when you have a loop, the number of times the loop goes around is controlled by the control variable. Now, in some circumstances, you may want to do what's called a premature loop exit, because in some circumstances, you would have a loop that would normally run for a very long time, but because of what you're doing, there may be the possibility of stopping early. All right, and here's an example of this. This looks very much like the divisor example that I showed you a few minutes ago. The only difference this time around is what we're actually doing is we're trying to determine whether or not a given number is prime. All right, and here's how this is going to work. We're going to start with the user entering the number that they would like to check, and then we're going to run through a range of possible divisors. We're going to start with n minus 1 and work our way all the way down through 2. And for each possible divisor we come to, we're going to see whether or not that divisor divides evenly into that number n. Now, since what we're trying to do here is we're basically trying to determine whether or not n is prime or not, as soon as we find a divisor that works, we can answer the question. And at that point, we don't have to continue looking at other divisors. We can actually stop. So what we do at this case is as soon as we find a divisor that works, we then execute this break command. All right, now what a break command does is if you're in the body of a loop and you execute a break statement, it causes you to immediately leave that loop. All right, so this is a way to jump out of a loop prematurely, and no matter what the loop control variable is doing, or no matter what the loop would otherwise do, as soon as you hit a break statement in a loop, you'll leave the loop completely and go on to whatever comes next. All right, and then finally, the last question here when we come out of the loop is how did we exit the loop? There are two ways to get out of this loop. One way is to let the loop run all the way to the end. And when it runs all the way to the end, what will happen is that d will be 1. All right, so if that happens, if the loop runs all the way to the end without hitting the break statement, we can test and see that d is equal to 1. If it made it all the way down to 1 without finding the divisor, that tells us that the number must have been prime because we never hit the break statement and we went all the way to the end. On the other hand, if we did hit the break statement, one consequence of that is that d will not be 1, and we can use that as a way of telling that the number is not prime, and in that case, we would enter the appropriate message here. Okay, so finally, let's run this with a few examples and see that it does the right thing. So let's enter a fairly large number. All right, so that's not prime. Let's try some other closely related examples like 1027. That's not prime. Let's just keep trying examples until we come up with something that actually is prime. Okay, primes get harder and harder to find as the numbers get bigger and bigger. Okay, there we go. We finally successfully hit a number that is prime. All right, and again, by having a loop to automate the process, which is very handy in this case because the number 1031 would require us to test a total of something like 1,030 different possible divisors. By automating that process, we can quickly zip through all that many divisors and determine that none of them work, and therefore that this number is prime. Right? So having the ability to automate stuff is a very powerful capability, and loops make this sort of thing possible. Okay, so that's the last of the examples that I would like to show you today. I'm going to come back with even more examples on Friday. And in the meantime, your work is to do the reading. Start reading at the beginning of chapter 5 and read up through section 5.9 to sort of reinforce what I did today and read all about the loops in Java. Okay, any final questions before we call it a day here? Okay, if not, have a good day. We'll see some of you in lab tomorrow and everybody else back in the lecture on Friday.